Hawaii, a tropical island in the Pacific Ocean, forged from volcanoes and teeming with diverse ecosystems, climates, and creatures. And for some, a laboratory for studying environments that could hold potential signs of ancient life on our neighboring planet, Mars. Four teams of scientists awake in the town of Hilo on the Big Island of Hawaii. They're not here for the beautiful beaches, the stunning waterfalls, or the lush rainforests. These astrobiologists are journeying to the volcano known as Mauna Loa to investigate lava tubes, caves formed by molten lava of past eruptions, to test a suite of instruments for future missions to Mars. After arriving near the summit, the team set out on foot across the barren lava fields towards their field site.
So this is a lava tube, which is a subterranean kind of environment. And so it's analogous potentially to sites on Mars that we've identified from orbit.
Mars is also a planet with a lot of basalt and obvious volcanism in the past. And we can see with imaging from space that there's things kind of like this skylight behind me that might be an entrance to a subterranean cavern.
And so if life potentially exists there, that would be a great place to live because it's isolated from the surface, which is very hazardous for anything to live. Here, these tubes are actually teeming with life. And so they could potentially be relevant to what we might see on Mars.
While all four teams have the same destination, they're all here for different reasons. Let's meet the teams.
My name is Dina Bauer. I am a research scientist at the University of Maryland and NASA Goddard Space Flight Center. So our role is to look at the relationships between microbes and minerals, to understand better what signatures are left behind by the microbes and the minerals, because on other planets we're more likely to see minerals as opposed to actual living microbes.
I'm Heather Graham from NASA Goddard Space Flight Center. We're actually trying to look for life by the geology itself. We're looking for mineralogical complexity on surfaces. We're also looking at elemental abundances, just the patterns and distributions of elements on those surfaces. And we're trying to use those two pieces of data to build up an energy landscape. So by looking at those minerals and those elements, we can calculate how much energy would be available for certain kinds of metabolism that microbes in these caves might use.
Over long periods of time, microbial life leaves a chemical footprint in the rocks. While it's unlikely that modern Mars has living microbes today, future missions can seek out these footprints to determine if there once was Martian life.
Yeah, so this is a really classic spectrum that you would hope to see on another planet because these are pigment peaks. So you're not necessarily getting specific in terms of species, but you can at least say there's definitely a microbe here. So we're doing a suite of measurements, a combination of what a rover would be doing and return sample analysis. Very quickly, Raman spectroscopy is a vibrational spectroscopy technique. Basically, you're firing a laser at your target, and that excites the bonds. Each mineral has its own signature because when the light hits those bonds, they excite differently and produce a spectrum. And so I use that spectra that I collect to tell me what minerals are there as well as what organics are there. So when we find them together, it kind of helps us understand their relationships. If the microbes are actually part of the precipitation of those minerals, we can infer that from looking at the Raman data. And on the flip side, if the minerals were there first and we do see signatures of the microbes, we might say that maybe those microbes are taking advantage of the elements and the energy present in those minerals.
Oh, okay, look at that. Got me some cave water. Got me some cave juice. Hey, Dina, I found water. Yeah, I'm getting your drips. We take all of these data that we're doing with field instruments and we're mapping this in a co-registered landscape of the surface. So I hate to admit that I actually learned about this technique by watching an archaeology television show, but this is a common technique that people do in caves so that they can have these co-registered maps of all of their different data types that they take for their measurements. And we're doing the same thing here. One, so that guy right there. And we have all of that information for all of those grids in the same place. Then we take that rock, we know each of those grid sections and all of that information about it. And then we're also taking portions of those mapped surfaces back to the lab to do measurements with much higher resolution laboratory instruments so that we can understand also not just testing the hypothesis of these patterns as a way to detect life, but also understanding if it would be possible to use a technique like this with the kind of instrumentation that we have flown on rovers and things like that.
I'm Dr. Ali Fox. I consider myself the anti-astrobiologist because I'm looking for biological patterns that are being produced by abiotic chemistry. The thing that keeps me up at night, my 3 a.m. wake-up thought, is that abiotic chemistry, so no life involved at all, can look a lot like biotic chemistry. And so when we're sending these rovers or these probes to these other planets and we have limited field instruments that we can use in those environments, we need to be really careful on how we can distinguish biosignatures. So a lot of the work that I do is trying to understand how abiotic chemistry can mimic those types of patterns. Okay, so I'm gonna be going right there. That's little. So I'm doing a combination of techniques that we can do in the field and then some techniques that we'll actually do back in our laboratory. So in the field, we're using an XRF, that's X-ray fluorescence, and that gives us an idea of what types of elements are present. So now it's switching to another beam that can actually see other types of elements, so it's adding a bunch in. So it's really helpful for me because it's not always clear from just looking at a rock that it's going to have really different mineralogy, but the difference in those elemental compositions, that tells us a lot about how that mineralogy is changing. So that's a quick, easy way for me to know that I'm getting the samples I'm interested in. And maybe in a couple of years, once I've recovered from being outside for this much, I'll be able to come back out and collect more samples.
Understanding the chemical makeup of these rocks will bring Dr. Fox and her team one step closer to identifying true signs of life from false positives.
My name is Bethany Teeling. I am a planetary research scientist at NASA's Goddard Space Flight Center. We are trying a technique that has been often considered but not explored as much. Can we identify life using the gases that we collect from the environment?
Basically, all life breathes, and life gives a particular signature of CO2 versus geological processes. So we can come down here and we can make a bunch of measurements of the ambient area and back in little crevices and get an idea whether there is life in the crevices or whether this is just ambient CO2.
One of the things we recognize is that it's a lot easier to sample gases. I mean, if you think about it, if you have to take one of these rocks around here, you have to crush it up and probably put it in acid and do a lot of stuff, a lot of chemistry before you can actually analyze it. With the gas, you can send it directly into an instrument and get hopefully some results. So we're trying something new here. We're trying to figure out if you can use the isotopes of carbon dioxide and methane to see if we can identify the life that we know is already here. So we've come up with a few unique and very new sampling strategies. One that I think is very fun is called the lasso technique. So we have this incredibly long tube. I have gotten pretty good over the past few days at lassoing. I'll take a few coils in one hand and throw it into the back of an alcove because I don't want to go back there and breathe. So this is one technique where I can stay back, turn my head, and just throw it into the darkness. Oh my God, I'm actually getting pretty good at this. We also have a simple ambient measurement, so we can just pull from the air right next to us, and that gives us a sense of what it looks like with all of our team here and how that could affect everything. So we were fortunate enough to get in here before any of the other teams, and so we were able to sample hopefully very quickly in order to get the sense of what it looks like as a more pristine environment, or at least constrained with just my colleague Jennifer and I, yeah.
My name is Dr. Stephen Scheidt. I'm an associate research scientist at Howard University. I'm working with NASA Goddard Space Flight Center. One of the things we're trying to do here is not just understand this lava tube. We're not just trying to understand the minerals, the life, or the geology. We're trying to understand the whole system. What we've done is we sort of started from the top and worked our way down. We took unmanned aerial vehicles, we've mapped the surface, and we've come inside the tube and we've mapped with LiDAR. And now we have a physical model of outside and inside. That's a really cool way of combining data to understand a system.
Do 18 around to here.
Yeah, we're gonna start here.
My name's Zach Morse. I'm a postdoctoral research scientist at Howard University and NASA Goddard Space Flight Center. So we're mapping the interior of the tube using a specialized camera that collects long exposure shots of the interior of the cave while it's illuminated in UV light.
Once we find a site, we set up a tripod, and we have a special device that allows us to rotate the camera at known set angles. And the geometry is set up so that when we take these pictures, that they will stitch into a perfect photosphere, where you have an environment where you can virtually stand and rotate your environment around. So in that process, Zach first collects the LiDAR from that point. We have a quick mount that detaches. We put on a lighting system that shines white light and has the camera. And then after we do that photosphere, we take that LED panel off and we add this UV system.
And this helps us identify minerals or some biology that might fluoresce in UV that is hard to see with the naked eye. And our end goal is to create a full map of the tube that can also be viewed in augmented reality, so you can walk through the tube and see that data in situ as if it was projected on the walls with our light. One of the things that's really cool about this is once we have this full model of the tube, we can add digital assets anywhere in the tube. So if another team has collected samples or collected data in a location, we can add a virtual field flag. So we don't have to leave any physical markers in the tube. We can come back next year, and as long as the morphology is still the same, hold up the tablet and see exactly where samples were collected, where data was collected, and help guide future expeditions to this location.
Building this full virtual system will take time, but even the raw data was already paying off in collaboration with other teams.
It's interesting because we weren't entirely sure how those collaborations were going to happen before we came. There's someone who's looking for ATP, which is a tracer for biological material, and we were able to hand her an image that she could put on the iPad on her arm. It was so close to AR, augmented reality, that she could look at the colors, zoom in and look at features on the scale of millimeters to be able to tell whether or not she wanted to sample them or not.
I can find it, yeah. So this is the only one that I can actually see, but only after you guys your technology pointed it out. So on this screen, here's this green, bright green areas, these two.
Yeah.
So they are right here and right here.
Yeah.
I'm gonna concentrate right in the middle here.
So they were able to target specific colors in the UV, get different swabs, and measure the amount of biological activity on different colors that showed up that are visible in UV, but you wouldn't see with the naked eye.
It was a really great moment for all of us.
I love being underground. I think I'm deep down inside, one of the dwarves. I'm just missing a giant beard.
I love rocks, I love minerals, so it's just fascinating to be here for that reason. But I think the really cool thing about these environments is it is isolated from the surface, it's so quiet, it's a really chill kind of place to be, and there really is a lot going on, so there's just always something to see, always something to sample.
Well, I think just being out in the field is great. Just be able to collect your own samples. And this is super important because you need to see the environment, you need to see where they were collected and not just a little crush sample that they give you, and I can collect what I want and much more to do my analysis in the lab.
It's definitely a change. I'm normally sitting in a room of humming mass spectrometers by myself in the dark. It's still dark, so it's not that different. The main difference is I'm used to being able to get my results quickly, but it's really cool to actually be on the side of like collecting my own samples. That's not something that I've done in the past. So it's been cool to make the decisions in the field myself. And what we're hoping is that we'll get a really solid pilot data set from this work, and then we'll be able to come back and do a really in-depth expedition.
You know, you always hear about field sites and you see pictures, but there's nothing like actually coming to the site and taking your own samples and then being able to measure them. It's just, you can't replace that.
It's been fun and challenging at the same time. I'm super grateful to get to be here and explore this crazy environment. It's tough to bring everything in and out of the cave every day, but it's totally worth it. We get some really cool science that we've been sharing all week, and hopefully help other teams with their science too.
It's a reasonable analog for Mars because if you're looking all around you, this is all made out of basalt. This is all volcanic rock. Mars was very much volcanic in the past, and so this could be a really good area for that. We know that there are skylights. We know there are lava tubes on Mars, and so this is a really great area to try to test that.
When we think about geologic timescales, so like hundreds of millions of years, that's a long time for an organic molecule to survive. And for the most part, how they do it is by interacting with mineral surfaces. And some minerals, especially clay minerals, make a much better home for organic material, and it can protect them from a lot of different things. We've also done experiments in the lab that shows us it can also protect them from radiation, which is a big problem on a place like Mars.
So for a long time, we used to think about follow the water, because we have this understanding that most life is probably going to need water. It certainly does here. And so we thought that if we just follow the water, that's the most likely place to look for life or look for habitable places. But really, we're coming to this understanding that there's really a need to understand energy potential. Are there the kinds of materials in there that would provide nutrients and energy sources for microbiology?
So I think there should be a lot more work done, and hopefully a lot of sharing of data so we can have a really solid data set. So like when we do land on Mars eventually, we'll have a wealth of information to work with.
These kind of instruments that we're using here in the field are what we call high heritage, which just means we've had a lot of practice building them and sending them places and making measurements on other planets with them. We're trying to find new ways, new strategies of looking for interesting information with just that kind of data. We could use the similar instruments, say on Perseverance rover, in a place like this. We might be able to use those same patterns and those same tools and techniques to identify the presence of life, past or present, on another world.
As NASA looks towards a future where human astronauts land on the surface of Mars, difficult environments like these Hawaiian lava tubes will be prime candidates for human exploration. And the data collected from expeditions like this on Earth may one day lead to a discovery of past life on the red planet, Mars.